So what is the Ising model? So the Ising model, the idea is quite simple. Imagine you have magnets which can point up or down, right? Instead of north or south, let's call it up or down. So when you try to put two magnets together, what happens? They try to align, right? They actually try to anti-align, right? The north tries to be next to the south. But imagine this is a sort of magnet where they like to point in the same direction. When would this happen? If you have a big external electric field, right? And you put a bunch of little magnets, it's like me hanging out with Pakora and his friends and someone says treat, right? All the dogs rotate and look in that direction, right? So if you have some strong external magnetic field, these magnets will all point in that direction, right? So so you can either think of it as north-south or up-down, or you could just call it plus, 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 plus. If it's pointing like this, you could call it minus, 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 right? And the way these magnets behave depends on a range of things. Number one, it depends on what is their interaction energy. Like in real magnets, they like to be opposite of each other if there is no external magnetic field, right? They also depend on the strength of the external magnetic field. What else might this depend on? How do magnets point?
The number of neighbors that they have.
Let's say we restrict to first neighbor interaction, okay? A magnet looks only at its first neighbor. It will depend on the temperature, right? I mean, even going back to my Pakora example and the dog's example, they are all looking in one direction, but if it's really hot and they're excited, if they're a postman going or things like that, there could be environmental factors which completely screw up everything, right? So such a magnet, if you're willing to look at the H is equal to 0 case when there is no external magnetic field, and if you impose nearest neighbors like to be similar, which is not always true. You could have and I will write things down mathematically. I want to motivate the problem first. If nearest neighbors like to be similar, and if you have zero magnetic field, then at low temperature, the system will look like this or like this. It's degenerate, right? There is zero magnetic field. You cannot tell the difference. As you increase the temperature and take it to infinity, it's going to look super chaotic, right? Some will be up, some will be down. There will be all sorts of disorder. And here I'm drawing 1D magnets. This could be 2D magnets. This could be very high emission magnets. Another way to think about, so this model of magnets, which we, and once this is not Ising model. This is just a model of magnets. I'll write down what exactly is the Ising model. So what Ising model does is to write down an energy function describing such magnets. It says that a given spin, and the motivation was from magnets, but this applies to everything. People, I have friends working at Facebook Research in New York. They use it to model people using social media, and people use it to model voters. Up could be Republican, down could be Democrat. And maybe you only look at what your neighbor is doing. And maybe you decide to do exactly opposite of what your neighbor is doing. Maybe you decide to do exactly the same as what your neighbor is doing, right? People use it to model neurons in the brain, how things spike up and things like that. So everything can be. In my undergrad papers, I use this to model stacking faults in a crystal. And I will talk about that in just a moment. So the spin SI can be +1 if they are pointing up, or if pointing down, it will be -1, right? This is how we define it. So let me go to next page. So the microstate for such, and for now, I will just restrict to one-dimensional Ising model, just for with simplicity. The microstate for this system will be +1, -1, +1, +1, something like that, right? Depending, so this would correspond to up, down, up, something like this. So if you really want to characterize the system, everything, you write down a bunch of numbers like this. There's nothing special about +1 and -1. It could be 1 and 0. You could call it 5 and 4. Who cares? It's just, the thing is there are two numbers which distinguish this. So the energy of such a microstate in an Ising model, it is often also called the Hamiltonian of a system. And notice there is no kinetic energy now, okay? It's just some interaction energy. Will be given by a sum of two terms. Number one, how does every spin couple to an external magnetic field? So let's say we have a magnetic moment at any site, mu, and this is the site in the spin of a particular site, SI. So the first thing is, how does this couple to the external magnetic field? So if H is equal to 0, if there is no external magnetic field, this does not matter. Mu is the individual magnetic moment. You can just think of it as being +1. Don't worry about it too much right now. So you can see that if Hx is positive, then the energy will be minimized if SIs are also positive, right? If Hx is negative, energy will be minimized when Si is negative. So the Hx just forces the magnetic moments to align along that direction, right? It's kind of like the Earth's magnetic moment, which by the way flips every few 100,000 years or something.
It's chaotic.
It's chaotic, but then there are a lot of people who think it will be like doomsday when it flips the next time.
It'll be bad. The Earth's magnetic field.
He's really worried. Oh, what? Okay, that's the first one. And the second one is, how do spins talk to each other? So here I can write down a most generic interaction term where not just nearest neighbor talks to each other, but every spin talks to every other spin. Okay, that is something like this. So for this, I will have an interaction term J. Again, this can, so Hx can be positive or 0 or negative. J can be positive or negative. You can make J 0 also, but then it's an independent system, nothing fun. Then there is no fun, it's useless. So J can be positive or negative. And then every spin multiplied by every other spin. Okay. So let's focus on the case when Hx is equal to 0. Let's consider no external magnetic field. So in this case, the thing that I described to you earlier, that at 0 temperature things will point along each other, and at high temperatures they will be completely chaotic. And let's set mu is equal to 1. Okay. So in this case, E nu, the energy of a microstate, is minus J summation Si Sj for any I not equal to J. Now, if we want to focus only on nearest neighbor interaction, E nu can be written as minus J summation modulus of I minus J equal to 1 multiplied by Si Sj. Of summation over Si multiplied by Sj, right? So what does this mean? Modulus of I minus J equal to 1. This means I is equal to 1, J is equal to 2, I is equal to 5, J is equal to 4, I is equal to 8, J is equal to 7, right? They have to differ only by 1. So it's nearest neighbor interaction. So this is my nearest neighbor interaction. Now let's consider two cases. Case 1, J is equal to 1. If J is equal to 1, what is the ground? And I'm considering only a 1D Ising spin for now. If J is equal to 1, what is the lowest energy configuration? What minimizes the E nu value?
The number of magnets.
It's the same. It's the fixed number of magnets. Okay, let's say number of spins equal to n. Let's say that is fixed. So if J is equal to 1, E nu is equal to minus summation I minus J equal to 1. Huh?
Do it all at the same spin.
They all have to be of the same direction. It will be minimized if all are, since we are writing plus, 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 or minus, 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 minus. And you cannot distinguish between both of these, right? So when I was a sophomore, I wrote down a Monte Carlo code for this in MATLAB. And every once in a while, the system would like flip as a bulk from plus to minus. And that was like, I have a bug. And I went to my professor and he had no idea what was going on. That's the first time you must have all been through this at some point when you realize that you know more than the teacher, right? That was one of my moments. It's just degenerate. It's going to flip. Of course, as you increase the system size, these flips will become less and less likely, right? Because a lot of things have to move at the same time. So that's case 1 when J is equal to 1. Case 2, J is equal to minus 1. So now my Hamiltonian is plus summation Si Sj. If now I gave the same values of spin plus 1 to all the spins, then the total energy will be a very large positive number. So what will minimize the energy in this case?
They're all opposite.
They're all opposite signs. So how will it look like? Plus, minus, plus, minus, plus, minus. Does this have a name in magnetism? Antiferromagnet, right? It's anti. So this is antiferromagnet, and this one is ferromagnet. These are the terms people use. So so basically, given on the value of, depending on the value of J, you can get different behaviors. And you can talk about the magnetization of the system. Do one thing. I'm going to run out of battery. Magnet, when figured there, we'll figure it out. Magnetization of the system M is going to every spin and summing it up. Okay. So what is the value of M for the ferromagnetic case? It is plus N or minus N, right? And you can also define M per spin. If you divide M by N, then it becomes an intensive quantity. So it is plus 1 or minus 1. What is the value of M for antiferromagnet? Yeah.
I actually had a question.
Yeah, first, what is the value for antiferromagnet? 0, right? What's your question?
So does ferromagnetic and antiferromagnetic, does that refer to the value of J, or does that refer to like the
Arrangement of spins.
Okay.
J on its own does not decide what's going on, because you can have a whole phase diagram on this.
Okay, so it's ferromagnetic if all of the spins are aligned.
Yeah.
Regardless
Yeah,
of what J
yeah,
is.
yeah.
Okay.
So we can then, so this is the magnetization for a given arrangement of spins, right? But we are doing StatMech. We know that every microstate has a certain probability associated with it, right? So as the spins keep fluctuating, the magnetization will change. So maybe we should be more interested in the average magnetization. Average magnetization, like average of anything in StatMech, will be going to every microstate, looking at the probability of that microstate, and looking at the magnetization in that microstate, right? So if we work in canonical ensemble, this will be e to the power minus beta E nu divided by the partition function divided by M nu. And E nu is what we wrote above, and this is a double summation. If you look at it, it's sort of complicated, right? This is I minus J is equal to 1, J Si dot Fj divided by Q, whole thing multiplied by mu, right? So this is a complicated summation. But it has some very interesting properties. And the whole game in Ising models is to calculate how does this M depend on beta? How does M change with temperature? What is the dependence of magnetization on temperature? What is the dependence of the fluctuations of the magnetization and temperature and things like that? So before I get into the math, I want to show you the key results that we will be studying over the next few classes. So if I plot average magnetization divided by N versus temperature, and let's say we are working with J is equal to 1, okay? We simplify our lives. What do you expect this to be at 0 temperature? Should it be 0? Should it be plus 1? Vivian, what do you think? For J is equal to plus 1 case, so the ferromagnet case, where we know the ground state is ferromagnet. Plus 1. If it was antiferromagnet, it should be 0, right? So this is a ferromagnet, and at very high temperature, it's going to be 0. So the question is, what happens in the middle? In the middle, it looks something like this. There is a temperature at which the average magnetization becomes 0. This temperature is known as the critical temperature. So at T less than Tc, you have a ferromagnet. There could be disorder. So you see how the magnetic, because entropy will prevail, right? So there will be some spins which are like, I really don't want to be perfect. The perfect magnetization only at 0 temperature. But as you increase the temperature, it will go down. As you reach Tc, there will be a temperature at which it becomes 0. Above here, you have a paramagnet. Paramagnet means, and if these terms confuse you, you can just call it ordered versus disordered, right? So the question people asked around 100 years ago, particularly it was a PhD student by the name of Lars Onsauger, who was probably annoying his advisor a lot. So advisor said, why don't you go and calculate the value of critical temperature for Ising model on a square lattice? So this is a 2D Ising model, right? I showed you the 1D Ising model earlier, but you could have a 2D one where the interactions are between neighbors like this, okay? And Onsager went and did it on pen and paper, and that led to a Nobel Prize for him. Onsager showed for a 2D Ising model, the critical temperature is 2 by natural log of 1 plus square root of 2. And Chandler Chandler has an exercise problem where he walks you through the proof of this. It's kind of amazing that you can prove this. With what you have studied in this semester, you should be able to do it. It's not hard.
What are the dimensions of that?
In units of J. I took J is equal to 1, right? So we will be talking, right now I'm trying to give you intuition for what we're trying to do, right?
Wait,
So
so J units of Kelvin?
Don't worry about units for a moment, okay? Let's look at the qualitative behavior of the picture here, right? We will get to units. We are semi-physicists, right? We work in units where it's convenient for us for now. Then we will get to it. This is in 2D. The question is what happens in 1D? If you had a 1D Ising model, what would be the value of the critical temperature? What would be the value of the critical temperature in 3D Ising model? What would be the value of the critical temperature in 4D Ising model and 5D and 6D and 7D? In fact, one of the big legends in statistical physics used to be a professor here, Michael Fisher. He has papers in Physical Review Letters from 40 years ago with Ken Wilson, who got the Nobel Prize, with the most strangest title ever, values of critical temperature in 3.99 dimension. And I heard about that as a PhD student. I was like, what's he on, like pot or something? What's he talking about? No, they do a perturbative analysis in the number of dimensions. And turns out there are models which work perfectly for 4 dimensions, and then you do perturbation around it and things like that. So can anyone give me intuition, if you have, for this? And what I'm going to do for 2 minutes, screen share people, Zoom people, don't be worried. You won't see anything for 2 minutes because I really need to charge my iPad. I will be talking. I'm not drawing anything. So what do we expect the critical temperature to be? Should we expect the critical temperature to depend on the dimensions? Why or why not? And if yes, then how? Any intuitions from anyone?
Yeah, it should depend on the dimensions.
How? Why?
You have more neighbors in higher dimensions. And since they talk temperature, each one of them contributes to each.
So that's one way of looking at it, right? In high dimensions, maybe you have more neighbors. So it's, if you are saying be like your neighbors, you have just more neighbors pressuring you to be like them, right? So maybe the critical temperature should become higher, right? If you see this intuitively, right? If you have one neighbor, you have to, like, if you have 2 neighbors, you have to be like 2 people. If you have 8 neighbors, you have to be like 8 people. So if you do something that is different, you have to differ not just from 2 people, you have to differ from 8 people around you, right? And then this makes it, we see this in society, right? And like, imagine you're from a remote village in India and everyone talks to everyone. Everyone is everyone's neighbor. If you go and do something opposite, the whole village will descend upon you. Like, no, you can't do it like this, right? Or if you live in Iceland, who cares, right? Or Greenland, whatever, something like that. So I don't know if that gives you intuition, it does to me. So basically the idea is that as you increase dimensions to a first approximation, the number of neighbors goes up. And so we expect the critical temperature to become higher. So, okay, as we go from 2D to 3D to 4D to 5D, we keep expecting it to become higher. For this logic, in 1D, we expect the critical temperature to be lower than 2D, right? How much? Turns out to be 0. In 1D, the critical temperature is exactly 0 if you have nearest neighbor reaction, interaction. In fact, if you have second nearest neighbor reaction also, it will still be 0. You have to go to a system where there is really, really long range interaction to get critical temperature is equal to non-zero in 1D. This has profound consequences. If you're working on a material, you are not going to have phase transitions in 1D. So when people talk about carbon nanotubes and how you have some ordered phase and a disordered phase, if it's strictly 1D, and if there is localized interaction, it cannot show a stable phase. Again, you can think of it intuitively. Have you seen those games where, I think there are like YouTube videos on this where you have a stack of things piled together and someone has a whole chain of things going around the room, right? And he drops one little thing and the whole thing falls apart, right? The whole effect communicates through the whole system. So in a 1D, if you flip something, and we will see, basically that's what we are going to work with now. Like, why is it that in 1D the 0? Why is it that, and how to come up with ways to calculate this critical temperature in high dimensions and things like this. So if you had just or imagine like a Jenga, right? A 1D Jenga block, unless you are very skilled, if you pull something, it's going to probably fall apart, right? But if you had a stack of like 2D Jenga blocks and you pull something from here, it's more likely that something will still stay ordered in it, right? So, okay, I'll go back to screen sharing. We might have to do this. This has never happened to me. So in 1D Ising model, the critical temperature is equal to 0 for 1D unless infinitely long range interaction, which by the way is Coulombic interaction. Coulombic interaction ties down very, very slowly. So if you have charged things, you can have stable phases even in 1D. But if you don't have charged things, if you have only short range interactions, you cannot stabilize a phase in 1D. Any amount of thermal perturbation will be able to knock it off. Okay, in 2D, you have a phase transition, you have a critical temperature. As you go to higher dimensions, this is TC for 3D, it will become higher and higher and higher.
Sorry, excuse me, Dr. Tawari.
Yeah, go ahead.
Oh, I think the screen got unshared on Zoom.
Oh no, that is so unfortunate. My Zoom is a disaster today.
Thank you. It's okay.
You can see now, I hope.
Yes, it's no, thank
Okay,
you.
thanks for me. So, and the reason why the reason why Onsager got a Nobel Prize for this, and why there might be more Nobel Prizes, because calculating this average value of magnetization using this formula is a really, really hard problem, right? You cannot do this. You cannot use any tricks, especially if you have more interactions. So in 1D, I will show you how the critical temperature is 0. In 2D, I will show you something known as mean field theory, which does an okay job of giving you a critical temperature. My $1,000 Nobel Prize problem is, did I say 1,000 or 2,000?
2000, we don't win the Nobel Prize.
If you prove it and if you don't win it, right? And you have to, it has to be like in a proper peer-reviewed journal accepted. It should not be like you have a blog where you say like, I have proven Ising modeling. Don't become one of those people, okay? If you can calculate exact value of TC in 3D, there is no exact solution. It doesn't exist. No one has been able to do it. And mathematicians, physicists, people have tried to do it. Numerically, it is known for, and in 3D, of course, the critical temperature will depend on your lattice, right? As we saw, things depend on the number of neighbors, right? So if you have a square lattice, you have 4 neighbors. if you have a hexagonal lattice, you have 6 neighbors. So already you can expect the critical temperature will be higher, right? So the thing will depend on the geometry that you have. So in 3D, there is no analytical solution. Renormalization group theory kind of gets you close. Mean field theory, which will, so we will study, so we will do this through 3 types of arguments. The first thing we will study is known as a droplet argument, which is very intuitive and quite nice. Particularly, it has a name, the spelling I always forget. This is called Pearls, P-I-E-R-E-L-S, Pearls droplet argument. Then we will study mean field theory, which is more mathematical. Mean field theory gives you a phase transition. Mean field theory gives you a critical temperature non-zero even in 1 dimension. So it's wrong, but it becomes more and more accurate as you increase the dimensions. And third, we will do some intro to renormalization group theory. Yeah, someone had a question?
Yeah, what if we prove that there's no analytical solution for TC in 3 dimensions?
I will still give you $2,000 if you can prove that. I don't think that will be interesting. It might be like a Gödel problem. It's like I am lying type of situation. You know? It's neither true nor false. Clearly, you are motivated now. Good. Okay, so this battery thing is annoying me. Let's take a 5-minute break, okay? It's down to 2% again. So let's add some juice to it. Zoom people, I'm going to pause sharing and everything. We will meet in exactly 5 minutes. I will just go have a glass of water or something. So sorry about this. I think one student is watching recording later. They will be very puzzled, like the whole thing. Yesterday, I had a day in which my first meeting was on Zoom, my second meeting was on Google Meet, my third meeting was on WebEx, and then I had a Teams meeting. I'm still like recovering from it, and in-person meetings on top of it. It's so strange. So, this is the perfect ground state, right? And in 2D. So now let's say we decide to make a domain in this, right? A domain where the spins are ordered in some other direction. Let's say we flip this one to down, and we flip, Mr. Colored Chalk, there is no colored chalk. We flip this one to down, we flip this 2 to down, and this one also to down, and in the bottom row, I flip 4 of them to down. So I've created a boundary between phases of opposite spins, right? This is like if you were looking at a real material, this could be like a grain boundary in a crystal, okay? If the boundary has length L, what is the delta E for this system? And I'm talking about the length of the boundary. I'm not talking about the number of spins that have gone up or down, okay? So if the boundary has length L, what is the value of delta E? 2JL. Why divided by? That's 2JL. We are doing it a back of envelope calculation, okay? So think about it as the 1D case. In 1D case, L was always 2, right? One edge and the other edge of the domain. That's why we got the answer 4J. In this case, so let me define my L more carefully. L corresponds to the number of broken bonds. If the number of broken bonds is L, then the energy penalty is 2JL, correct? Same idea as that we had last time, right? Because we had this going to this at any boundary, right? So this was plus J, and now this is minus J. So the penalty is 2J. And if you have L bonds which are disrupted, the penalty is 2JL. So already something is interesting. We have a L term that is showing up. In the 1D case, there was no L term, right? It was always just 4J. It was boring. So something is happening. We have hope. But now the harder bit here is to calculate delta S. This is much harder, right? This is not just like placing thing in one place. This is like, how do we move in this space? What is delta S going to be? So do you see my screen, Zoom people? Do you see my handwriting inverted?
No,
It
it's
looks
normal.
Cool, here it looks inverted, which is strange. Delta S is going to be K, L, and W that we are fine with, but the problem is what is W? What are the number of ways in which we can create a boundary with L disrupted bounds? Any ideas? How should I calculate this thing? How should I proceed? Let's say let's say I have this one disrupted, right? In order to disrupt the next one, the question is how many ways can I pick up the next bond to disrupt, right? So in this particular case, or let's say I started over here. If this one is disrupted, in order to disrupt the next bond, I can move in this direction, top, right, bottom, or to the left, right? So I'm picking up the next interaction to disturb, right? But if I went from, if this is disrupted, like, color would have been useful here. Let me draw this once again. Let's draw a perfect lattice where everything is ordered. Let's say I have taken this one and made it point downwards. Okay, so this bond is broken. So the question now is, how do I pick the next bond to break? Okay, and we have lattice sites over here also. In this case, how many ways can I pick the next point? 4, right? So let's say I went to this one and I disrupted this one also. Oh, there is yellow, perfect. So this one was, no, it's not yellow. So given one, I can go to the next bond to disrupt in 4 ways, right? It could have been this one, this one, this one, and this one. Now comes the tricky part. How about now? Will it still be 4? Why not? If it was 4, I would go back and undisrupt this one, right? And that's clearly wrong. I won't be left with something. In other words, I have just shown that W has to be smaller than 4 to the power L, right? At the same time, W has to be more than 2 to the power L. Why? Because if you did only 2, that would mean you're only moving around one line, right? You would miss out on many other possibilities. So what lies between 2 to the power L and 4 to the power L? 3 to the power L, right? It's a back of the envelope calculation. So let's assume that W is 3 to the power L. And this, the other reason I love this argument is because this gets you within 30% of Onsager's Nobel Prize winning calculation. That's just mind-boggling, right? So let's assume W is 3 to the power L. And I will post some notes online which work through a more intuitive argument and actually calculate the value of W more carefully. So let's assume W is 3 to the power L. I'm now going to erase this spin so that people on Zoom can see. So we just have shown that delta A is 2Lj, right? Number of spins that are disrupted, number of bonds that are disrupted, minus kBT ln 3 to the power n, right? So what does this becomes? This becomes 2Lj minus LKBT ln 3, right? Or this becomes L 2J minus KBT ln 3. Very nice. So now if I plot delta A versus T, what is the value of delta A at T is equal to 0? It is 2J, right? So at T is equal to 0, the Helmholtz free energy is positive if you want to create a domain for any value of L. It's not going to happen. At T is equal to 0, if you create a domain, it will be like, I don't like it. I want to stay where I am. If T tends to infinity, what will happen to this thing? It will become negative, right? So now you get a behavior which looks like this. You actually have a critical temperature that exists in this system. This value over here is Tc. What will be the value of Tc? It will be when 2J minus KBT ln 3 is equal to 0, right? So Tc is equal to 2J by KB ln 3. This is approximate for square lattice in 2D. What was Onsager's Nobel Prize winning answer? That was Tc is equal to 2J by KB ln of square root 2 plus 1. Anyone remembers the value of square root of 2? 4, 1.414. So 1.414 plus 1 is how much? 2.4. That's remarkably close through our hand-waving argument, right? We got to that. So this is the Pearl's droplet argument. You can extend it to 3D also. Of course, your life becomes a bit harder in calculating the value of W. Here, I could just be like, well, it's less than 4 to the power L, it's more than 2 to the power L. It's actually 2.4 to the power L. It's something like 2.5. And the article that I will post online, you can get remarkably close to 2.5 by thinking geometrically. But that's too hard for me. I'm happy with this. It's getting so close. I mean, this is like 30% error in the critical temperature. And you might be like, oh, 30% sounds horrible. Well, next we will do mean field theory, which is infinitely wrong in 1D. Mean field theory gives a behavior like this even in 1D. But mean field theory becomes more and more precise as you go to higher temperatures. Mean field theory is also one of those things in statistical physics which is super relevant because that's how machine learning models are trained. By assuming things very similar to mean field theory. There's a lot that goes on in statistical physics. These ideas have like basically come back in machine learning in the last 20 years. People, the computer scientists don't even realize what they're doing has been there in statistical mechanics for a very, very long time. And you can see why, because when we talk about spins like this, it is not very different from neurons in a neural network, right? I'm looking at collective behaviors of how things are arranged and things like that. So I'm going to pause here. Any questions about this?
So, calculate the average value of magnetization.
No, we did not. We just calculated the value of the critical temperature. First droplet argument is not giving you the M versus T curve.
Yeah, but the critical temperature was defined for average magnetization coefficient.
But it is also defined as the value at which the free energy becomes 0 between the ordered phase and the disordered. These are the two same things. So critical temperature was defined at which we see the transition from ordered to disordered, right? So per construction, critical temperature is the temperature at which two phases can coexist, right? And two phases coexisting means that Helmholtz free energy difference is 0, right? They can, because if the Helmholtz free energy is positive, it means one of them will exist, the other one will not exist. You will be able to go spontaneously from one phase to another phase, right? So I'm appealing to a bit of thermodynamics here to do this. When we go to mean field theory, we will actually work with average value of any magnetization. We will plot it. That's what renormalization group theory is even stranger. There we'll be looking at flows and strange all sorts of things. Okay, so I'll pause here. Sorry about the iPad debacle, but it turned out to be okay. And I like this thing a lot. It's a lot of fun. I hope this is something you will remember like 20, 30 years from now. It's not too hard, right? It's a simple argument and it gets you within 20% of a Nobel Prize.